Welcome to lecture 16, which is on black body, because there are many objects which we treat as a black body and use that characteristics in remote sensing, and also the atmospheric window. So, in this lecture we will understand what are those wavelength region which are particularly useful to carry out the remote sensing based study. So, let us begin with this lecture. You must have heard this term black body in physics. This black body term was introduced by Kirchhoff in 1860. We consider that it is an ideal body which can absorb all the electromagnetic radiations that falls on it. So, in previous lecture we were discussing the absorption phenomena. So, here is the body, black body, which can absorb everything, all the electromagnetic radiations which are falling onto the surface of this, and no electromagnetic radiation passes through it and none is reflected back. While in remote sensing, when we were discussing, our main focus is the maximum reflectance, but black body concept is totally reverse here. It will absorb everything and nothing will be reflected back and nothing will pass through it. So, because no light is reflected or transmitted, so object obviously will appear as a black. Okay. So, this is the concept of that black body which is used actually to derive certain relationship, because the sun we are considering as a black body. So, black body is the ideal source that can transform the heat energy into radiant energy. When it absorbs the energy, naturally there will be some changes which will take place internally in the black body itself. Either the temperature will rise, or it will change its shape, or it will change its size. Some changes are going to take place there. So, it is the ideal source that will transform the heat energy into the radiant energy. And when the maximum rate permitted by the thermodynamics law, we can relate the two together, the temperature and the wavelength region. Like a piece of iron, if you keep in the sun for a while, it becomes quite hot to touch. So, it has absorbed certain temperature. So, maybe there is a relationship between the temperature of the body and the wavelength. Similarly, if I keep a piece of wood, and that will not be too hot to touch, we can still touch that, but piece of iron probably cannot touch because it has absorbed lots of incident energy which is falling on it. So, a black body will emit a temperature dependent spectrum of the lights. That means if I heat that piece of iron, it will radiate the energy. So, we have seen that the piece of iron, if you are heating it more, that if you increase the temperature, heat it, it becomes red hot and it radiates lot of energy also. You feel heat when you are standing close by. So, black body emits the temperature also whenever required. It depends upon the wavelength region. So, we are using the thermal radiations from the black body, and we call it the black body radiation. So, we are using these properties that every object will emit some kind of energy, and it depends upon the temperature of the object. At room temperature, for example, the black body emits mostly infrared light, but if you increase the temperature, then they start to emit the visible part of the wavelength region, red, orange or yellow or white, before ending up to blue, beyond which the emission includes increasing amount of ultraviolet light also. So, when you are heating it up and you are increasing the temperature, then you will find that there are certain bodies will change the color, and all objects, irrespective of their color, irrespective of their shape, above absolute 0 Kelvin, they emit energy in the form of the electromagnetic radiation, and that is why, because of this emission also, because they are emitting the energy, we are able to see the objects. We can have a feeling of the color of the object, shape of the object, maybe a texture of the object, because the object is emitting the energy to our eye. A black body is considered the perfect emitter. That means it will absorb all the energy and it will emit all the energy as and when required. So, body does not have to appear black in the color. So, this is a wrong concept that probably a object which appears black in color will be termed as the black body. Sun and earth, they are approximately behaving like a black body. So, we consider the sun as well as the earth. Earth is also emitting the energy. So, sun acts as a black body at 6000 degree Kelvin temperature. So, outer surface temperature, that will be 6000, and it is radiating the energy at maximum possible rate, and it is reaching to the earth surface. So, if we look at the black body radiations at different temperature, because the temperature of the earth will be much lower than the sun. So, energy emitted by all the matter and the objects above absolute zero temperature. So, here we can see that in the table there are examples of 4 different temperature ranging from 1000 to 4000, and if we take the different wavelength region, then the relative intensity of the emitted energy will be different. So, both energy and maximum frequency, they are basically dependent upon the temperature. As the temperature is increasing 1000 to 4000, the total intensity has also increased. We have come to 0.4 from 0.0003, and it is shifting higher energy from visible part to the ultraviolet part of the spectrum. That is what we have seen. So, this is the case which is going up like that, or as far as the wavelength is concerned. So, there is a relationship between the three. Now, if I draw the wavelength on the x axis and spectral emittance, the emitted energy on the y axis, I can see the curve of a black body and curve of a water. So, they are more or less resembling the shape of the curve following parallel, except there is a small variation here. So, the firm line denotes the black body, whereas the water body is denoted by the dashed line. So, we can say that water is a good approximation of a black body. It is following similar to the black body. Now, if we say the quartz, okay. So, again we have a curve for the black body at different wavelength region, and we have curve for the quartz material. So, we can say in the selected part it is a good approximation, but here in this part of the wavelength region now it is not following the similar curve as the black body, its behavior is different. So, in a selective part of the wavelength region it is following the black body. Now, this is a very important diagram, and this diagram shows that if we have the wavelength on x axis and spectral emittance on y axis, and also a third parameter which is the change in the temperature. If we change the temperature of the body, if an object we take and heat up that object and change the temperature, what will happen actually to the amount of energy. So, these different shapes of the curves are indicating that ranging from 6000 degree Kelvin, which is the temperature of the sun, black body radiation curve at the sun temperature will be the highest peak, and the maximum peak is in the visible part of the spectrum. But if we look at the different kind of a, if we see the earth temperature, which is here 300 degree Kelvin, which is the earth surface temperature, peak is there, but peak has shifted to the higher wavelength region. So, in this curve we can see intermediate curves are also drawn at different temperatures. So, if we raise the temperature like a lamp, okay, black body radiation curve at 3000 degree Kelvin. The peak is somewhere between the two, sun and the earth. So this diagram is showing me that the peak radiation, emitted radiation, will shift from lower wavelength to the higher wavelength. So if I join the peaks, I will have a curve something like this. So the peak is shifting from higher wavelength region to the lower wavelength region as you increase the temperature, and based on that certain relationship can be derived, and people have derived certain laws on the basis of this curve. And since the peak is displaced, so very popular law which is called Wien's displacement law has also been devised. So there is a relationship now between the temperature, the wavelength region and the spectral emittance. So let us see that. So there are law of radiation. When we are talking of the electromagnetic radiations, we know that the wavelength and velocity of the light and the frequency, they are correlated with each other. But when we are talking of the electromagnetic energy, which is consists of the photons or quantas, particles, the energy which the photon or these particles carry from one place to another in the form of the wavelength, it can be related with this relationship. E is equal to h into f, where h is the Planck's constant. It is a known, it is a fixed quantity, it is known, and f here is the frequency of the wavelength in which we are working. So if I know the frequency, I can find out how much is the energy which is carried by that. So if the frequency is higher, the energy is higher. If the frequency is lower, the energy is lower. So we can see in case of X-rays and gamma rays, because of the higher frequency of these X-rays, gamma rays, cosmic rays, the energy carried by these particles, photon and electrons, this is much higher as compared to if we take about the visible part of the spectrum or the higher part of the spectrum where the frequency becomes lower. So because of the high amount of energy which is carried by those X-rays and gamma rays and the cosmic rays, they are able to penetrate into the human body also, and that is why you can get the skeleton of the body in medical science, and you have to expose your body just for a fraction of the seconds, otherwise it will be a very much deeper penetration and damage the body also. So we are using the same concept now in our remote sensing. E is equal to h into f, and we know that the frequency of the wavelength we can replace by c upon lambda. We know that f is equal to c upon lambda, where c is the velocity of the light. So all the radiations are travelling equal to the velocity of the light. So I can replace f here by c upon lambda. So h and c here in this relationship, they are two constant quantity. So these are the two constants. So I can say the energy which is carried by the particles, it is inversely proportional to the wavelength. It means the capacity of electromagnetic energy to work is directly proportional to the frequency or inversely proportional to the wavelength region. So shorter wavelength will carry more and more energy. Shorter wavelength means again the X-rays and gamma rays as compared to the visible part of the spectrum. So this is the radiation law. Then in this curve, the wavelength is drawn on x-axis, different wavelength region, and the power, the energy is on the y-axis. So we can see here using the Planck's law. Planck has given a very important mathematical equation which is written over here, and different terms are defined where h is the Planck's constant, c is the velocity of the light, lambda is the wavelength of the radiation, k, there is one more constant here, k is the Stefan-Boltzmann constant, and T is the absolute temperature of the radiating body or maybe the black body. So if you see these curves again here, at different temperature. So, we can see the energy also is maximum in the visible part of the spectrum. So, energy which is carried out is also in the visible part of the electromagnetic spectrum. So, this is a very useful then part, visible part for our remote sensing based study. Then there is one more law which is called Kirchhoff's law, and Kirchhoff's law says that all black bodies at the same temperature, the ratio of the emitted energy to the absorbed energy is same. So, here we have taken the ratio of the two energies, the emitted radiations and to the absorbed radiation remain same at the same temperature, all black bodies will behave same. So, this is defined in terms of the emissivity. Emissivity can be computed is the ratio of the two things here, m upon mb, where m is the emittance, emitted energy, and mb is the emittance of the black body. So, we can define the amount of energy which is carried out or the visibility of the object on the image in terms of the emissivity also. So, we can we know the emissivity of the different objects, you can see in this particular table here. So, different materials here are shown from silver, copper, gold, because they are all found on the surface, wood, asphalt pavement, paint, vegetation cover, white paper, water, black paint. So, they have all different emissivity values, right. So, this emissivity value is a measure basically how strongly it interacts with the radiations in terms of the emission or in terms of the absorption. Two processes, absorption will take place and emittance will take place. Okay. If both are equal, the emissivity will be 1. So, we can have for different objects which are found on the earth surface and we are taking the images from the different sensor, they may have their emissivity value ranging from 0 and 1 and depends upon the frequency or the wavelength on which we are capturing that particular data. So, all the objects will have the values ranging from 0 to 1. What is the meaning of that? Meaning of that is that the maximum value 1 would imply that the incident radiation is completely absorbed at a given temperature and completely emitted also. That is why the value is 1 of that particular ratio, completely absorbed and completely emitted as and when required, and this is what the definition of the perfect black body is. So, black body will have emissivity 1, and if I show you the previous table again, there is nothing like a black body here. The value is not 1, but they are closer to 1 if we are talking of the black paint or the water body. So, high emissivity comes together with the high absorptance value. Higher absorptance means the object would appear to us darker when we are talking of the images. Object will lesser emissivity, emit less light or scatter the more light. So, that concept actually now we are using in remote sensing data analysis. There is very famous law here, Wien's displacement law, and it is related to the diagram which I have shown you, that the peak is displayed from the higher temperature to the lower temperature towards the higher wavelength region. So, if we make a relationship between the wavelength, what is the maximum wavelength at which the peak is occurring in terms of its absolute temperature of the object, we can correlate the two together, that lambda max, maximum wavelength at which the peak is there, it is inversely related to the absolute temperature. Here B here is a constant quantity. So, lambda max is equal to B by T and B is a Wien's displacement constant. So, its value is also fixed constant quantity. So that means this state say as the temperature of the object increases, the wavelength of the maximum emittance also increases. That is what we are getting from this Wien's displacement relationship. Now this is one example here which is shown that different temperatures, at different temperature the peak is shown to you at earth temperature and at sun temperature. So we have taken 6000 actually at the temperature of the sun body and 300 as the earth radiation, and if we put up in the Wien's displacement relationship, so maximum peak will appear at 0.48 micrometer wavelength region. And when we are talking of the earth temperature at 300 degree, then the peak comes out to be at 9.7, which is somewhere here we are talking of 9.7 micrometer particular region. So sun is radiating its maximum energy in the visible part, this is 0.48 micrometers. So this is the visible part of the spectrum where the maximum energy is emitted, and the earth is radiating its maximum energy in the infrared portion, because this is a 9.7 micrometer region. So if we take the images in the infrared part of the spectrum, that would be very useful to carry out the temperature related studies. There is another law which is called here the Stefan-Boltzmann law, and according to this law, this states that the black body will emit the energy per unit area in relation to its temperature. So it is directly proportional to the fourth power of the temperature. So M is the total energy which is emitted by a black body, and it is directly proportional to the fourth power of the temperature, where T is in degree Kelvin and sigma here is a Stefan-Boltzmann constant. So it is again a fixed quantity. So what it says is that as the temperature increases, okay, then the radiated energy would increase many folds because of this relationship. So let us work out at the sun level, energy at the sun, which will come out to be 7.3 into 10 to the power 7, and energy at the earth will come out to be 459. If we substitute the value of the temperature here, temperature of the sun body and temperature of the earth body, as we have taken in the previous example the temperature, the same temperature we are taking here. So if we calculate the energy, one comes out to be 7.3 into 10 to the power 7 and another comes out to be 459, and this gives us a clue that the energy at the sun is 160,000 times higher than while the temperature is 20 times higher. While the temperature of the sun is only 20 times higher, but the energy is much higher, and it is following the Stefan-Boltzmann law. Then there is a very important term which is atmospheric window in remote sensing. Once we know all those laws which are to be followed by the black body, then we have to find out which are the regions in the atmosphere where the electromagnetic radiation can pass through and reach the object without much of the losses, without almost no loss. So the ability of the atmosphere to transmit the entire radiation is called the transmittivity. So we want those regions where transmittivity is approximately 100%, and this also will vary depending upon the wavelength region which we are using. So we have to find out those regions, and those clear regions where the transmittance is more higher as compared to the surrounding region, those regions are called atmospheric window. In fact, this window is like a opening. So we have the windows in the house where the air can pass through. So similarly, windows in the atmosphere are those regions where the reflected energy can straight away pass through, reach the object without any loss. So, this is a very famous diagram of atmospheric window, and which shows that if we draw on x axis the wavelength region and transmission, on y axis we can see that there are certain regions where transmission is maximum, and there are certain regions where there is absolutely no transmissions, absorption is more. So, for example, this region where absorption is quite high, but this is the region where the transmission is very good. Then again we have a microwave region, we have some infrared regions where the transmittance is good, atmospheric losses are good. So, we have to identify those wavelength regions with the help of this diagram, so that we can work out, we can take the satellite images, we can design the sensor and carry out our analysis using those images where transmittance is good. So, we are talking about the different gases now which are present here. So, see, you can see on x axis there are different gases which are shown, and transmittance is also shown at different wavelength region. With respect to the wavelength region, the transmittance is also shown. So, there are gas molecules, atmospheric particles which are present, and then there are processes which are taking place. So, identify what are those best wavelength region where loss due to transmittance, loss due to absorption, and loss due to scattering is minimum. So, if we look at the region, probably what happens is wavelength shorter than 0.1 micrometer, it is absorbed by nitrogen and other gas components. This we derived from the previous diagram. Then we have the wavelength which is shorter than 0.3 micrometer, X-rays, gamma rays, they are mostly absorbed by the ozone layers. Then we have visible part of the spectrum which is 0.4 to 0.7 micrometer wavelength region, there little absorption is occurring. Then we have oxygen which is present in the atmosphere, absorption is centered around 6.3 micrometer wavelength region. Then we have the infrared part of the radiation which is mainly absorbed by water vapor and carbon dioxide molecules which are present, and then far infrared region mostly absorbed by the atmosphere, and then microwave region absorption is almost nil. So, now with this wavelength region and looking at the diagram which I showed you, we can find out the wavelength region which are very good to us in order to carry out the study. So, here now we can see that there are some regions which are very good, visible part is very good, then we have this peak near the infrared part, middle infrared part. So, these are those peaks where sensor could be designed, sensor could operate in order to take the data. So, visible part in a way and the infrared part of the region, they are the good regions where they are mostly unaffected. Then also the microwave part of the region. So, you can see here in the microwave part of the region also the transmittance is very good, losses are minimum. So, these are the three regions: visible part, thermal infrared part region, infrared part region, and the microwave regions, they are the best. So, this diagram shows the visible part of the spectrum where this is a complete, it is reaching to the ground. Then there are infrared windows, okay, these windows which are completely reaching to the ground, the incident radiations, and then we have the other part of the microwave windows. So, these are those suitable regions, and these regions are called atmospheric window region. So, we have to remember the wavelength region of these regions, because they are very useful in remote sensing based study, whether we are using the data in the visible part of the spectrum, whether we want to study the data taken in the infrared part of the spectrum or the microwave part of the spectrum. Not all the wavelength regions of infrared, not all the wavelength region of microwave regions are useful to us, but there are few pockets which are very useful to us. So, this particular table is showing us that we have ultraviolet, visible and photographic, then reflected infrared, thermal infrared and microwave region. So, these are those approximate regions where the transmission is given, the characteristics 95% transmission is there if we are talking about 0.3 to 1 micrometer wavelength region, and then reflected infrared we have 3 regions 1.3, 1.6 and 2.5 micrometer region. These are the 3 narrow bands. If the sensor is designed into 3 narrow bands, they are very useful to us. Then thermal infrared we have 2 big regions, one is 3 to 5 micrometer and 8 to 14 micrometer. These are the 2 broad bands. So, if we are talking of the thermal infrared images, the sensor, if they are designed to operate in this wavelength part, they can detect the thermal changes. Then microwave 1 millimeter to 1 meter, the atmosphere is mostly transparent. So, these atmospheric window regions are very helpful to us in order to carry out the correct selection of the data. Now, utility of these regions are important so that we know that here the atmospheric losses are minimum and we are expected to get, because the transmission is maximum, we are expected to get the good reflectance from these objects, and these objects as far as the images are concerned, these objects would be much clear to us. The images will not be hazy type of images. And secondly is that if we are collecting the data from the radiometer, field based instrumentation, so these are those regions where with confidence we can collect the data, and also if we are designing a sensor, the sensor should operate in this wavelength region to give us the maximum information content. So, this is all about this lecture. Thank you.